Hello. This is the first talk in the CropsTV series of this winter. The first one, we talk about lime and pH management. The others, we will talk about P&K and nitrogen later on. Lime, I think, is important because when the prices are bad, the first thing that farmers cut is lime application. Then they may cut P&K, and seldom they will cut nitrogen. But lime is important, and we should consider it, and with some special considerations when the crop prices are low or the lime prices are high. Okay. Let's do some short review of some basic concepts, which I think is useful. The soil acidity, of course, is bad for crops, and the effects are because of are direct by impairing root cells function. High hydrogen concentration cause that, but most of the time is an indirect effect by increasing levels of toxic elements, such as aluminum, for example, with very low pH, decreasing nitrogen fixation by legumes, and then decreasing the availability of some nutrients. Now, the long-term causes, if we're talking about tens of years or hundreds of years, is the natural leaching and uptake of cations, especially in humid regions like Iowa. And also acid rain due to pollution, which, by the way, has been decreasing over the last 20, 30 years. But the short-term causes, so let's say if we're talking in a period of 2 years, 4, 5, 6, 10, is the application of ammonium or ammonium-forming fertilizers. Okay, some sulfur fertilizers, but not gypsum, and then some manures, mainly liquid swine manure, because often has very high concentration of ammonia. Now, this is a chart that I don't remember the name of the professor that made it. I think it was in the 40s or early 50s. It is qualitative, It shows, approximately, roughly, the impact of soil pH on different nutrients. So we have there nitrogen, and honestly, I don't know if this considers nitrogen fixation or just availability of nitrogen in the soil, phosphorus, potassium, et cetera, et cetera. So we have this very low pH 4 on the left and high pH alkaline on the right, okay? And then we have the different nutrients there. Now, remember that in Iowa, when we have alkaline soils, it's because of calcium carbonate, and the pH seldom is more than 8.2 or 8.3. Okay. Now, in the Great Plains and in other areas of the states, we can have sodium-affected soils, and in those soils, the pH can go even actually higher than 9. It can be up to pH 10. Okay. So this is a general thing, and I put those vertical lines there. So you see the red vertical lines. That really, the impact of pH in the availability of nutrients is clear, either good or bad, when there is an extreme pH. Say, if we have pH, say, below 5, 5.5, something like that, then most of the nutrients we have reduced availability. If we have pH over 8, some nutrients, we have reduced availability, such as iron, manganese, boron, copper, and zinc, etc. Okay, so people tend to think that because they have pH 5.8 or 5.7, oh, that's horrible, because of the availability of phosphorus, this and that. And it may be bad, for the legumes, for nitrogen fixation. But normally, between about pH 5.6, 5.7, and 7 is not much, really, the impact of the pH variation. Now, as I said before, the short-term soil acidification. is mainly due to fertilization with ammonium containing fertilizer and manure. This is because the transformation of ammonia to nitrate that occurs in the soil and is mediated by microorganisms releases hydrogen ions, and that acidifies. Now, by pound of product, and there are some charts over there that I didn't include it here, ammonium sulfate is the one that acidifies the most because it has the ammonium and also sulfate there. And then it's followed by MAP, DAP, anhydrous ammonia, urea, or liquid soy manure, and UAN. But you see, this by pound acidification really is not much relevant because several of these fertilizers that contain, for example, sulfur or phosphorus are applied based on the sulfur need of crops or the phosphorus need of crops. So the important thing really is the application rate, okay? Now, of the sulfur fertilizers, elemental sulfur acidifies soil because its oxidation of microorganisms to sulfate releases hydrogen ions, okay? But normally, people that apply elemental sulfur, I mean, we need about 20, 30 pounds of sulfur for element for crops. So that doesn't acidify much. Now, gypsum, this is a common mistake in many people. Gypsum does not change pH. We have lots of data about that in non-sodic soils. Now, in soils that are affected by sodium, that we don't have naturally in Iowa, then sometimes when the soil has good drainage, gypsum is recommended and reduces pH because the calcium exchanges with the sodium, okay? And then this favors the leaching of sodium from the soil, and this reduces pH. Now, why is that lime neutralizes soil acidity? Okay, those limey materials that have carbonates, like a lime, pelleted lime, or eggshells, increase soil pH because they have the calcium carbonates, okay? Soil pH is also increased by application of quicklime, or it's called also burn lime, which is calcium oxide, plant residue ash, which has not just calcium or magnesium oxide, but also potassium and sodium oxides, hydrated lime, which is calcium hydroxide, and the lime residue from the water treatment plants, that they have calcium or some magnesium carbonate and also hydroxides, okay? So these materials react with the hydrogen in the solution, okay? And that produces calcium or magnesium-free cations, water, and in the materials that have carbonates, carbon dioxide gas. So the key to the increasing pH is not only the calcium and the magnesium, but the partial elimination of hydrogen from the solution or reduction of hydrogen in the soil solution by producing water or both water and carbon dioxide in the case of the carbonates. Okay, now the neutralizing value of the different liming materials varies greatly across different materials. And there are two concepts here that are important to remember. One measurement that is done in ag lime or other materials is the calcium carbonate equivalent, okay? This is the acid neutralizing value compared to pure finely ground calcium carbonate, okay? And is measured in the lab by dissolution with a strong acid. And this method is about the same in all states, the same method. However, what happened is that the particle size distribution, that's the fineness of a liming material, affects the solubility in the soil and the time it takes since the application to increase soil pH to a desirable value, okay? So you know that very well. There are limes there that are very fine, others that are very coarse, and so forth. So we have the effective calcium carbonate equivalent measurement, okay? So what this is that combines the calcium carbonate the calcium carbonate equivalent, the CCE, with an estimate of the material effectiveness according to the proportion of particles of different fineness. Okay, so in Iowa, IDALS has been requiring for, I don't know, the last 3-4 decades that all lime materials sold in Iowa should be analyzed by a method that it is specified that sieves the material through 3 Tyler screen mesh sizes, 4, 8, and 60. Now, in other states, they do the same thing, but they call it different. Some call it neutralization capacity or something like that. Now, honestly, we here at Iowa State, even my senior peers that retired or passed away already, didn't have a clue where these efficiency factors that are there came from. And we did some research here. We published a paper, I think it was in Agronomy Journal, that actually they're pretty good. These sizes and these things is done, except, as I said, as you will see, they may overestimate a little bit the efficiency of dolomitic lime. So you will see that. Now, other states use these same sieves or a couple of different ones, but the concept is about the same. Okay, so you should not apply lime based on the tons of product, tons of ag lime or tons of whatever, of pelleted lime or whatever, okay? You should apply based on ECCE, okay? And the information that we have in PM 1688 about this says that, okay? Now, is another important basic thing, and there is much confusion out there, because everybody knows that, we measure pH and buffer pH, but some people still don't understand, of course, how it's measured, which is not that important in this talk, but for what each of those is used and how it should be used. So soil pH is the active acidity, okay, in the soil solution. And this is what should be used to decide if lime is needed or not, okay? Now, soils have some capacity to counteract the lime application effect by releasing additional hydrogen ions. And this is called potential or reserve acidity, which tends to be higher in soils that have high clay or organic matter content. So the soils with high clay and high organic matter have a higher capacity to resist a pH change. So they will need more lime to affect a certain pH change. So the buffer pH is used in the United States to determine the amount of lime needed to raise soil pH to a desired level, okay? Essentially what it is in the lab, mix a buffered solution of known pH with a very strong buffer with soil and measure the pH decrease from the original buffer solution. And the methods used to be the SMP, doesn't matter what it means, but lately it's mostly the Sicora method that is used in Iowa, but the results are the same. So that little scheme shows that when how the soil pH, the pH of the buffer, and the pH of the soil plus the buffer solution relate. So that green difference is the reserve soil acidity. And of course, this need to be calibrated in different soils and with lime application in order to determine the amount of lime needed to increase the pH to some level, okay? So pH is useful to decide if we need lime or not. The buffer pH gives us the lime requirement and how many pounds of lime should be applied, okay? Now, Iowa has a very long history of pH and lime research. I put there in the 40s, but I believe there were some research even in the 20s or the 30s, until the 60s, okay? And those were used to establish the ISU liming guidelines that were in Iowa. Now, in the middle 2000s, several questions started to come up out there about the adequacy of existing guidelines. So, for example, on-farm strip trials in central Iowa with corn and soybean show little or no response to lime, even though pH was 5.5, 5.6 or so. These were trials done mainly by the Iowa Soybean Association Farm Network, just simple trials without. And then with my student, Agustin Bianchini, we did some experiments looking at sampling methods and comparison of uniform versus variable rate application. Now, all long-term trials that were still being conducted, mainly by Dr. Henning, and some short-term trials by Paul Castle, Sawyer, and I believe John Holmes, I didn't put in there, now retired, all of them. Several research farms were showing very variable yield results across Iowa. Another question, especially people from eastern Iowa, were asking about what about the difference between calcitic and dolomitic lime, because there are a quarry or two in eastern Iowa. There's dolomitic lime. It doesn't have much magnesium, but people call it dolomitic lime. Then pelleted lime. The sale of pelleted lime increased a lot over the last few years. And then finally, questions were, since the recommendations have not been updated since the late 60s, and the state of Iowa, IDALS, requires a certain method to evaluate the effective calcium carbonate of the materials, if this method was still good about that, okay? So we did some research about that. Now, this is an example of this research that we did with Bianchini. We have two fields in central Iowa, and we were 2 years. This on the left, okay, we have the soil pH after liming for, these were strip trials, managed with precision ag technologies. And so what I did there, I divided the data for the field in 3 areas that initially have pH less than 5.7, 5.7 to 6.2, and then 6.3 to 7.2. Those were the pH of the areas that we observed there. Now the red bars for each pH group is the soil pH using variable rate, and the yellow bar is using just a uniform rate based on soil testing. So what we can see is that in the lower initial pH ranges, the pH after liming is higher with the variable rate, the red bars, than with the uniform rate, the yellow bars, because of course in the acidic areas we put more lime with the variable rate. But when the initial pH was 6.3 to 7.2, we increased more the pH with a uniform rate, because still we're applying more there, but with the variable rate we apply less. Now, the graph in the middle shows the amount of ECC, effective calcium carbonate, applied, and I put there tons per acre. That's what it is, ECC. So we apply less lime with the variable rate, just because the other was uniform according to an average pH, but the variable rate we were applying more or less depending on the initial pH. Now on the right, we see that these are the net returns using prices at the time. And the net returns to lime application, of course, we measure yield, I'm not showing yield, were negative, because mostly there was no yield response. So what they were saying, they were right, you see. So now with the variable rate, the losses were less because we apply less, okay, than there. So now the Iowa, the liming recommendations have been saying for a long time that in central Iowa, north central Iowa, mainly soils with calcareous subsoil, the optimum pH can be lower than in other areas, okay? So this is not too surprising, but the fact that there was no response even in areas that were less than 5.7, I think the lower was 5.4, the pH. That was something that created many questions. So because of that, we began mainly with the funding of the Soybean Association. This study, this very large study that we conducted in 14 fields, we applied, we did it with my PhD student, Agustin Pagani. We apply yes, no lime. We put 0 or 3 tons ECCE. And we have it in different counties, and we use lime for several queries, but the lime application was based on ECCE was the same. Okay, we use grid sampling, there were strip trials, we use GPH, GIS, etc. The idea was to identify optimal soil pH for corn and soybean, not necessarily what is the lime that gives the highest yield. And at the same time, we wanted to study the potential of variable rates. And another major objective was because, honestly, I didn't believe much this idea that with a subsoil, with calcareous subsoil, the optimum pH in the top was less than for subsoils with acidic subsoil. So we spent lots of money trying to look into this. So we have the 14 fields. We measure yield, corn soybean rotations over 4 years, and we apply lime only at the beginning. I'm not going to go to details. Okay, this is a across the board summary of the yield results. And because the yield levels were different, of course, in different years and different sites, what this shows on the y-axis is the yield, the relative yield response percent. So those are not bushel. For example, 10 is 10% response over the control that received no lime. Okay, so the right graph, the left graph is corn across all fields and years, and also sections of fields with different pHs, okay? And the right graph is soybean. So the pH range goes from 5 equal or lower than 5, and the highest 7.5 or higher. Those are the ranges for those bars. The line, the vertical lines within each bar indicates the significance, okay, of that length of the bar if it is different from 0, okay? That's what it shows. So what we see with corn is that there are yield increases until the range of 6.5 to 6.9, but this is not significantly different from 0. And the increase for corn from 6 to 6.4 is not significant from 0 either. Okay, and then the increase in the 6 to 6.4 is a bit less than 2%. Okay, so that in normal corn this year could be 3-4 bushels. Okay, then after pH 6.9, then we do have a yield decrease, although in these two cases were not statistically significant, but it's clearly that in pH 7, above pH 7, if we apply lime, most likely that will reduce yield. In soybean, we see more variability, but about the same trend. But the impact of the for some reason from 7 to 7.4 of the yield decrease, you know, is more marked. Now, take a look at the percent increases. See, of course, the prices are different, you see. A certain percent increase of corn, it may not mean the same thing that a certain percent increase in soybean, but in terms of the relative response, the response of corn and soybean is about the same, you see, in acidic soils. So people have this idea that it's mostly in soybean that requires lime. No, corn also needs lime. Now here we did the same thing across all sites, but we put in the left graph those data for the soil association areas that had low subsoil pH, okay, acidic subsoil pH. And then on the right, those data for those sites where the subsoil had high pH down to a depth of about 3 feet. See, this is what the Iowa State guidelines have been saying since the late 60s. Okay, and what we prove, of course, this is just averages, that they were right, you see. If you look at now I put here corn and soybean together, okay. If you look at the graph on the left with acidic subsoil, there is a response up to pH, the range of 6.5 to 6.9, okay, although might not be statistically significant. And we didn't have sites with corn that had sites that had higher pH in the top. So we don't have data for 7 to 7.5. Now, on the right, the graph in the right, these are the data for the soils of soil association areas that had calcareous subsoil, okay? And we see that the response, even in very acidic soils, is less than for the others. And the other was almost 10%. Here is about 6%. And we clearly see that there is absolutely no yield response after pH 5.9. So with pH, if we apply lime in these soils, there is no response, or it can actually decrease yield. That already was shown in the previous slide. Now, I have this Agustin Pagani, PhD student, losing hair, and me too, studying, doing all kind of analysis and things, trying to explain why this happened. And the old-timers have not explained, and I cannot explain either. For some reason, there is less response when we have calcareous subsoil. Okay, now, it is clear from this research, and it's the first that I know that was in Iowa, that when we apply lime to calcareous soils, we may not affect yield, but we may decrease yield, okay? And this is very common in central Iowa, northern Iowa. Now, Greg Tilka from plant pathology has been studying soybean cyst nematode for a long time, and we worked together years ago on calcareous soils, and it's clear that the soybean cyst nematodes really like high pH soils, and I believe that if we apply lime, that may actually aggravate this issue. So it is important not to apply lime in calcareous soils. Another result from this study that I could prove to you if I could show the results for all the 14 trials, and this was a surprise for Sawyer mainly, not for me, because I had been working in lime in Uruguay 35 years ago, is that the ag lime impact at increasing pH is faster than people believe out there. People believe, yeah, you apply lime, and then the maximum pH may not be reached after 2, 3, or 4 years. Bull manure. That's not the case. There was absolutely no trials, those 14, that we observed that. In all trials, the maximum pH was reached at the first year, 1 year after application, or the second year, okay? And then began to decrease. And we use lime for 5, 6 queries, applied based on ECCE. So another important thing is that we have some fields with no-till management. And we were getting all kind of questions about how deep, the lime effect is, what should we do, and so forth. I have done lots of research with alfalfa in Uruguay. And then I have shown, that the lime in alfalfa, when it is applied after seeding, does not change pH below about 2.5, 3 inches, but here there was no data that I know of with that have this study with also yield response. So these are averages across the no-till sites, and what we show is that in the soil pH after liming, from a depth of 0 to 3 inches on the left and 3 to 6 inches on the right. And then the different bar colors are the years. The white, first white bar is the initial, the black is after 1 year, then after the second, third, and fourth year. So it is clear that the lime does not move much below 3 inches, and even the little bit of increase is mainly in the first year, not much in the other years, okay? So this brings us to the issue of the soil sampling and interpretations. It's clear that there was a major lime effect increase in pH only in the top 3 inches of soil, smaller and short-lasting effects deeper. Now, if you look at our extension publication, PM 1688, we have the lime together with P&K guidelines, and then Crop 3108 is the soil sampling that we updated with Sawyer about 2-3 years ago. So what we say there is that sample from no-till and pasture, sample the top 2-3 inches for pH and lime requirement, okay? Because that's the soil volume that for sure can be changed. This has been the recommendation in Iowa since the 50s, okay? Now, the issue is that seldom the acidity in the deeper depths really affects the yield response to be a problem. You see, we thought, for example, that with continuous anhydrous application, we may have an acidic layer about 5-6 inches, but it's not too clear. And then if we put too high lime rate in the topsoil, that may be a problem. It may increase micronutrient deficiencies, problems with herbicides, and so forth. But we recognize that almost nobody does this. You see, everybody samples about 6 inches for PK lime or whatever. So we said in that publication that people could also take 6-inch samples. But if the lime application rate is calculated to neutralize pH down to 6 inches, then need to reduce the lime rate by 1/2, okay? Because otherwise, this will be applying too much lime, okay? So should apply the rate by half, and then check pH in a couple of years. I wouldn't go to sleep, and don't check pH for 4, 5, 6 years, just in case, okay? See, this is important because there is lots of confusion out there. There is no clear communication sometimes between the guy that takes the samples, the farmer, the lab, and whoever makes the recommendation. So you need to be careful, because if you sample 6 inches from no-tiller pasture, and then you use the recommendation to increase pH to 6 or 6.5 to that depth, then you're applying double the lime needed, and of course, it will not pay. Okay, concerning the sampling, these are two graphs that I got from the publication, Crop 3108. Essentially there we discuss sampling, not just for pH and lime, but for PK. And then we have the sampling by soil type and topography on the left, and an example of grid sampling on the right. You can take a look, at the publication in terms of what it means. But the point I want to make is that when we have high pH variability, when we have a mix of acidic and calcareous soils, like in central to north central Iowa and southern Minnesota, not even a good 2.5 acre grid sampling may be good enough. See, this is some data that shows these were the strip trials. So I just selected 2 strips that we have like transects. So we measure pH in composite samples taken every 10 feet. And then those are the black points. And then the red points are that we took samples, a composite every 200 feet or so. Okay, so look at the variability. These are the black points. in this area. You can go from pH 5.5 to pH almost 8 over 50, 80 feet. So, and then in this case, we were amazingly lucky because we took the sample before we knew the results. And look at the red points, how they match pretty well when we took the sample with the transect. But I mean, it would have been enough that we had moved, 40, 50 feet, we would have got, a completely different number. So this is a problem. So this is why it's important that we use aerial images or somehow identify where these calcareous soils are. We can use something bad, which is the soybean iron chlorosis, in order to see where these sites are. And I remember Fred Blackmer, now he passed away years ago, and his students were talking about this many years ago. And this data shows that it's good. Now, most Iowa fields, they are not all calcareous. We have like the north, the top graph is soybean year, and then the bottom graph is the corn year, the following year. And we can see that we can very clearly see those are the calcareous spots. And even in corn, we can see them. Probably it's because there is more volatilization or leaching of nitrogen there. That's why also showing corn. But the issue is that even with a grid sampling, taking 10, 15 cores, 2.5 acres, it's enough that you get most cores from the acidic area and get one core from the calcareous area, that screw up the sample result. So I think people should be very careful and when sampling, and then, of course, try to apply lime in the acidic areas, but not in the calcareous area. Now, this is something that it's very obvious. Don't apply lime in calcareous soils. So I think that with variable rate you can fix this some. Now, of course, some of the applicators for lime are so wide that cannot micromanage small areas. But I think we do better management. Okay, the other question that we got, we did some research, was about calcitic and dolomitic lime. And so from 2009 to 2010, we have 4 2-year trials. We have acidic soils in 4 areas of Iowa. And we have several treatments. We put no lime, pure calcium carbonate, finely ground, calcitic lime, and dolomitic lime. The calcitic lime was from a quarry in central Iowa, and the dolomitic was from a quarry in eastern Iowa. And then we took soil samples many times over the 2 years. And I will not give too much details. There is no time. So these are the results of the lime, the application sources and rate on soil pH. Okay, so this curve sounds weird because you see that the black goes up to 10 tons of ECCE, almost 10, but the blue only about 4. This is because we apply the lime based on CCE, not ECCE. Okay, and the ECCE was different. Okay, so that's why. But this thing shows that, of course, the pure calcium carbonate was much better, and then the maximum pH across the different sites was achieved within 80 or 100 days. The calcitic lime was very close to the calcium carbonate, and the maximum pH in some fields was achieved at 80 days, but sometimes 150 days. And the dolomitic lime, it took a bit longer. The maximum pH was achieved between 90 and 150 days in some fields. But we can see that clearly the ECCE method, we use the one that IDALS requires, overestimated the value of the dolomitic lime. Okay, not much, but it did. So it means that a certain ECCE means is about okay for the calcitic lime, but for the dolomitic lime, maybe it's overestimated a bit the effective calcium carbonate content. We also have incubations in soil that we confirm this. Now this is the yield, okay? And these are across the 4 trials. In the left is soybean, and the right is corn. So we have the ECC rate, and the different colors of the points are the sources used. So you see there is essentially no clear difference between the sources. Now, the lowest rate was 1 ton of ECC, okay? So in the case of soybean, we achieve maximum yield with about 5 tons of CCE, and in the corn with about 4 tons. But there is no rate differences between there was no source difference, okay? So even though what we show here for the dolomitic lime, given the rates needed to get these yield levels, that wasn't an issue, okay? So the results show that there is no much difference in yield, although the current method, and I never talk to idols about this, because we use only one dolomitic lime. So in order to be sure to change the methods of the interpretation, we should use some more dolomitic limes from different quarries, just to be sure. Now, this has been shown in some eastern states, okay? Now, this is because the magnesium carbonate dissolves slightly slower than calcitic lime, okay? But the main issue is that the dolomitic lime usually tends to be coarser than the calcitic lime. It happened in our study, and often happens out there. But this, as I said, this difference wasn't a big deal, because that didn't translate in really much difference, for the yield. Now, some people are saying, that in eastern Iowa there is excess magnesium. There is absolutely no confirmation of that, no evidence for that. There is no deficiency of magnesium either. Now, the dolomitic lime adds magnesium. So in some states where there is magnesium deficiency, that could be good. Okay, in addition to that, from 2015-2016, we did some research with pelleted lime. This was, we did 2-year trials, 6 2-year trials. We used rates of calcium carbonate, calcitic lime, and pelleted lime. The pelleted lime is the one that is being sold in Iowa. It's sold by calcium products, and the material is from the Gilmore City and Fort Dodge quarries. And the difference with some other pelleted limes that were in the past in some other parts of the United States is that these guys really grind the limestone very fine, okay, before the pelleting, okay? So I just want to acknowledge the research was done with support by the Calcium Products, Martin Marietta, and the ISU College of Research Farms. Okay, so this is the pelleted lime that we use, okay? So we have tons of data. What I'm showing here in these 2 graphs is the effect of the sources and rate on soil pH after the application. On the left graph, we apply this in the fall, okay? And then we sample before planting, okay? So about 4 or 5 months after the application. And the right, these are the samples, we took several soil samples over time. So this is at the time that the maximum pH was attained by each material, which was about 100 to 150 days. So what we see here is that in the left graph, we see that the points for the pure calcium carbonate and the pelleted lime are essentially exactly the same, okay? But the red points, which is the ag lime, are much lower. Now, this makes sense, okay? Because the ag lime, of course, needs a bit more time to react. It was only 4 or 5 times. But this shows that the pelleted lime is darn good. It's essentially the same as a pure calcium carbonate powder, okay? And then on the right, we have at the maximum pH. Now the differences between the ag lime and the pelleted lime and the calcium carbonate are not that big. They're about the same. So, but this shows that these granules really dissolve well. You know, we did it with we applied with field cultivation. You know, but really works. And here we have the yields. On the left we have the corn yield, and on the right the soybean yield. See, again, the different symbols and colors show the different sources. There was absolutely no differences between the sources, okay? Now, the lowest rate was, again, 1 ton of ECCE, okay? So, yes, we have this issue, we have the difference in ECCE, but in terms of the yield, with these rates, that didn't make a difference. Okay, so because of this research, we started a new research now. This is funded by Calcium Products. That the idea was to look at strategies for pelleted lime application, because some salesmen say, yeah, put pelleted lime, just put about 500 pounds, you know, blah, blah, blah. Well, we have doubts about it, you know, because by pound of ECCE, then the effect should be the same if the ECCE measurement is right, okay? And then pelleted lime is more expensive than lime. So we did all this research, and I have the data only for 2020. We broadcast before corn. For 2021, we have a soybean, and in 2021, we divided all plots in 2 halves to study the residual effects of the first-year applications and the effect of new applications. Okay, so this is just a quick average. The results were kind of similar. All soils were acidic. And the graph on the left showed the grain yield response. You see, as we expected, the higher the application rate, the higher the yield increase. Now note that I put a break in the x-axis between the 1,600 pounds and the 6,400 pounds rates, okay? Because otherwise, you know, it would be too wide. So in general then, very low rates of 100 and 200 pounds of pelleted lime, yes, increased pH, increased grain yield, but we needed at least 1,600 pounds or 1,800 pounds on average in order to get the highest yield. And on the chart on the right, we have the soil pH. So we suspected rates of 100, 200 pounds essentially did not increase much. But we can see there was a small effect on yield. Now, the jury is out, you see, because I honestly, I have not seen yet the results for this year harvest. So when we put together the results for the initial applications and for the double applications, then the annual application, then we can say, you know, more about it. Okay, so the Iowa guidelines were last updated in 2013 based on the data that I show until then. Essentially, there was almost no change because this confirms the old-timers data. They were right, okay? The optimum pHs were right. Now, we work with corn and soybean. I did not work with grass clover mixtures or alfalfa grass. This is in PM 1688. So the use of the salt pH of major aggregated soil association is good to define the optimum pH for corn and soybean. The only change you see is that in corn and soybean, we say that with high subsoil pH, the optimum pH is 6, with low subsoil pH is 6.5. And we suggest applying lime to raise pH to 6 or 6.5. So the difference with the old recommendation is that even though the optimum pH for these 2 areas were 6 and 6.5, they still recommended apply lime to increase pH to 6.5 with high subsoil pH. And we believe that didn't make sense at all, okay? So we changed that. Then the other thing we did, we included variable rate equations so people could use variable rate, you know. And this is the map that is in PM 1688, showing the colored areas are where soil association areas have calcareous subsoil. And so it's essentially central, north central Iowa, and western Iowa. This is a table. Of course, you cannot see very well these numbers, but this is the table in PM 1688 that we have according to buffer pH, okay? And then several options, how much ECCE or pure calcium carbonate should be applied for different sampling dates, okay? And different target pH because of the different crops. So the overall conclusion about the prices is that they need to apply according to the price by ton of ECCE. That's the key, okay? The ECCE of ag lime varies widely in Iowa. I mean, it goes from about 1,100 to 1,800 pounds per ton, okay? And then, but pelleted lime is almost ECCE, is almost essentially 2,000 pounds, so it's good. Now, the price per ton of ECCE varies a lot in Iowa, and I did a survey with our field agronomist to give me some idea of the prices, but I decided not to use any because it's just incredible. I mean, it's just, the difference are 2-3 times. So, with good over prices, what can people do? Okay, the first thing is do a good sampling, okay, apply based on ECCE, okay, use the buffer pH to decide the rate applied, and look at the sampling depth. Now, when prices are bad, okay, and not everybody may agree with this. I think that with bad prices, if a buffer pH calls for 5, 6, 7, 8 tons of ECCE, that could happen in some soil with high organic matter or fine texture and very acid. I think it doesn't make sense to apply all that amount. See, given the results that I show there, I would apply 2, 3, 4 tons, because that essentially will maximize the yield of the first crop or the second crop, and then apply the rest, take soil samples, say 2 years later, and then apply more if it is needed, okay? Now, some people that own the land and they are okay, and they could apply 8, 10, 12 tons of ECC, whatever it is, and then don't need to worry for several years. But I think that because the soil sampling is not perfect, the buffer pH measurement is not perfect, and then the investment all at once, that people could apply just 2, 3, 4 tons, and then apply the rest, later on, not necessarily all at once. So with that, I'm sorry that I cannot take questions here, but there is my phone number. You can call me, and you can also send email. And I remember that we have this soil fertility website that was started by John Sawyer and I. Sawyer retired, and I'm continuing updating it. So there is lots of information by line. And then the 2 key publications, extension publications with guidelines are PM 1688 and Crop 3108. Thank you so much. Bye.